Can you hear us? People online, can you hear us? Hello? Can you hear us? Yes, great.
Yeah.
Okay, so let me also press. So welcome everyone who covers CMSA coming up in that this seminar series. We're very delighted and happy to have Guanyu Zhu from IBM content. You'll be speaking about, for example, fault-tolerant quantum computation by topological order on fractals and emergent symmetries. So the people online, please let us know if the camera of this microphone is working well. And let me remind the audience, please feel free to ask questions. If you want to speak with one day or so. Okay, let's welcome Guanyu.
Thanks, Drew, for the introduction. Thanks, CMSA for the invitation for giving the talk. Yeah, so I'm going to talk about fault-tolerant quantum computing. With talk about the order on fractals and the emergent symmetries. What do we do? Oh. Sorry, there are some technical. kind of
Yeah, there was whatever things.
okay. Sorry for the interruption. Was technical. Yeah. So I want to begin the talk with some famous quotes. And first, there's Ralph Nader sitting in the hallway of IBM, Heights, and he said information is physical. And there's the opposite view from John Wheeler, said from it. So this opposite kind of views will play some roles in this talk. And here the outline of this talk. So in part one, I'm going to talk about topological order and quantum codes on fractal geometries. Should get to these two papers and in collaboration with Apida and Thomas Joshua Kona. And in the second part of the talk, I will talk about how to do fault-tolerant logical gates on these fractal codes and also described in this paper. And then further, there is some interesting connection to emergent K-form symmetries and codimension K+1 form defects.
The screen sharing here.
It's
not a
oh, but that's well.
I think you need to stop sharing and then share the other screen.
Let me just do this.
Yeah, so right now it's the issue that the screen share on Zoom and screen share on the is display in the seminar room is it's not the.
Can you hear me?
It's not the synchronized. It's not the same mode. But I guess we can just use that one. It's okay, I guess.
Okay, you're good.
And maybe we can continue in this way.
Okay, then I'll do this. Yeah.
Right now it looks the same, but once we share the full screen.
Yeah. Okay, I'll just stand here. In this mode, it will work.
Almost.
Yeah, that one is. Let me just okay, this is Sorry for the interruption. So yeah, so yeah, the second part talk about its also its connection to emergent K-form symmetries and four-dimensional K+1 defects, and some general theory of these defects, which are discussed in this paper in collaboration with Mason, Yuan, Shenjie, Rohi, and Nat. Okay, so so first, let me talk about a little bit about the roadmap of quantum computing from IBM. So we are currently here, and we have last year we have already realized that superconnect chip with 400-ish qubits, and then the goal is there should be some sort of a more slow growth of the number of qubits, and at later than 2026, we should have 10,000 to 100,000 qubits. However, the major challenge is that you need to reduce the qubit overhead for doing some useful quantum algorithms, such like Shor's algorithm, quantum chemistry simulation, or even quantum machine learning. But typically they may need lots of qubits to the standard surface code approach. Like you may need 1 million qubits, but we need to significantly reduce it. And also, in the long term, we just want to improve the scaling of fault-tolerant quantum computing. And the major challenge for the standard surface code approach is that they can only do fault-tolerant logical Clifford gates. And these Clifford gates can only map Pauli operators to Pauli operators. So they cannot be universal. Then you need the additional, very resource costly procedure called magic state distillation, which could use more than 99% of your space-time resource. So it's less efficient. So that's one of the major challenges. Okay, so the motivation of this talk. So first, we want to understand the topological order and the codes, and in general long-range entanglement on fractal geometry beyond the usual scenario of a manifold. So, so here is some example of fractals embedded in 2 and 3 dimensions. So this is the Stravinsky carpet, which has a fractal dimension 1.893. So the fractal dimension characterizes how the size of the system scales with the linear system size. And also another example is a Munger sponge embedding 3 dimension, has fractal dimension 2.727, and the fractal dimension in this case is all smaller than the embedded dimension. Actually, another thinker, Mandelbrot, who was basically the founder of fractals, even he has already thought about, when he was at IBM, he thought about making classical self-correcting memory on an Ising model supported on a Stravinsky carpet, which is embedded in 2 dimensions. So here we ask whether just generalize this kind of a line of thought, that whether a fractal quantum memory could also exist in nature. In nature, which means whether it's embeddable in 3 dimensions. So then, from the practical side, we want, as I said, on this roadmap, we want to significantly reduce the space overhead, especially for implementing non-Clifford logical gates with topological stabilizer codes. So there is actually a trade-off between dimensionality and universality called the Rabi-Koenig bound. So it says that logical gates implemented by a constant depth local circuit in n-dimensional topological stabilizer code has to lie in the nth level of Clifford hierarchy. So, for example, the second level is just the usual Clifford group. So that's why surface code can only do Clifford gates. So in order to do non-Clifford gate, you need to at least go to 3 dimension. So here is our basic idea. It's a sort of a code puncturing idea. So we could reduce the total number of qubits or the volume while still preserving the code distance and the logical gates. So in this way that we can replace the integer dimensions node scaling L to the D to the scaling with the Hausdorff or the fractal dimension. So that could also improve the distance scaling as the number of qubits. So in particular, you can reduce the space overhead of implementing a logical CCC gate, which is a class of non-Clifford gates. Originally, it needed order L to the L cube qubits for 3D surface code, where L is the linear size. And now we could replace this 3 with a Hausdorff dimension. So it could go to, for example, 2 plus epsilon, and the epsilon approaches 0. So another question is, besides doing non-Clifford logical gates, 3-dimensional topological code also has property of single shot error correction, in the sense that unlike 2D surface code, you need to do D rounds of measurement to correct errors. In 3D topological code, you could do a single shot error correction. And we are wondering whether this could also be the overhead could also be reduced, such that the Hausdorff dimension is smaller than 3. Okay. 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 So, success switch. Yeah. You can share some. Yeah, but it's not happening. Okay.
Okay, great. We're back again. So let's stand wherever you want. Where do you want to stand? Yeah. Okay, great. I think both sides right now works. Sorry for the delay.
Yeah. So but in this talk we will focus more on the aspect of logical gates instead of single short error correction. So there's still yet another motivation is that while studying this certain exotic fault-tolerant logical gates in quantum error correction, it actually inspired us to develop some systematic theories of certain higher form symmetries and responding invertible defects. So it's kind of the idea from quantum information is the idea of quantum information actually provides some inspiration for condensed matter physics and topological field theory. Okay, so let me start part one of the talk about this this stuff. Yeah. So let me first define quantum error correcting code. So the definition of a quantum error correcting code is that to encode the logical qubits in a large collection of physical qubits. So here is a logical subspace or the code space, which is a subspace of the full Hilbert space of n qubits. And the most common code used in the community is the stabilizer code, and that's defined with a set of stabilizer generators form a stabilizer group. This stabilizer generators commute with each other. So the code space is just a stabilizer subspace, and which the subspace satisfies that they have a common +1 argument of any of the stabilizers. So one can also encode the code space into the ground state subspace of a certain parent Hamiltonian that you just put the minus of sum of all the stabilizer generators. So the ground state will just be the code space. And then one can define the so-called code distance D, which is the minimum support of operators that take one logical state to another logical state. Basically, is the minimum error that can cause logical error to the code. So here, in order to understand the topological order defined on fractal geometry, so we could use a quantum information perspective to define topological order, which is, for example, discussing this paper. So one can define topological order as a local physical system with ground state subspace from a quantum error correcting code with a macroscopic code distance D. So this means there's exists D scales at the power law of the linear system size, and for sufficient large system size L, while you sandwich any local operator with a projector to the ground space, it's and proportional to the projector. So here is an example of a local operator. So and it has it support less than the distance D. So for example, if I have a complete loop, then it will have a kind of the distance D. So the operator should be smaller than that. So this definition is also equivalent to a more traditional definition in condensed matter literature that you can consider the matrix elements of this local operator between the two different logical states labeled by A and B. So it's basically there is no off-diagonal elements unless this OA reach the size of the O distance. So in this way, the code state or the ground state is protected against any local area. Also, that's the origin of topologically protected ground state degeneracy. So yeah, so this kind of you can understand the property of quantum matter from a quantum information point from it. Now, so this work is actually has connection between several different fields. So the co-distance D here is actually related to a geometrical property called systolic, which is the shortest non-contractible cycle of a metric space. So here is the illustration. So this shortest cycle on this torus here is this group of the size D. So one can say that if there's no topological, if the distance is of order 1, which means it's not it's microscopic instead of being macroscopic, and there's no topological order existing in this system. So yeah, in general, this connection between different fields is between the topological order, quantum error correcting code, and also systolical geometry. So as I said, the protected degeneracy responds to macroscopic distance, and the geometry means a macroscopic systole, and it's related to relative homology when there is boundaries. And the stability against large spatial disorder, for example, in the case of fractal, as related to the protection against fabrication errors or code puncturing in the context of quantum error correcting code. And also in the second part of the talk, the interesting connection between fault-tolerant logical gates in quantum error correcting code to global and higher form symmetries in topological order, and also related to sweep certain gap domain walls of defects. And then there's also we will see in some cases we can get codes with a non-poly stabilizer, and they respond to certain exotic gap boundary topological order. Okay. Okay. Yeah. So yeah, let's start. So okay. So first, I want to talk about a no-go theorem for fractals embedded in 2 dimension. So here the most familiar case in the audience in quantum error correction is the service code or toric code. So in the service code, you have additional gap boundaries, and there are typically there are two very common boundaries, which is the so-called E boundary, which condense E aliens, and there is a logical Z string can be terminated on this type of boundary. And then there's a M boundary where logical X will terminate on that. So now we start to dig holes iteratively to define a fractal. So this is a serpentine copied fractal, where this SC31 means that we dig hole with a ratio between the system size and hole in each iteration would be 3 versus 1. And then this L means the level of iteration. So in the iteration, it's just surface code, but then you do one hole and then smaller and smaller holes. So it turns out these holes could encode logical information because they can trap logical strings. So then you ask whether it's a blessing occurs. So the thing is that when you introduce hole, you have these strings surrounding this hole, and then X string terminating this hole. And when you keep doing the iteration to such that the smallest hole is of the lattice constant of the system size, then you will see that the original macroscopic logical string will always cross with a very short string of order 1 length, and they anti-commute. So that just means an error of this order 1 size could just flip your logical Z operator and change your logical operation. So in this case, you only have a microscopic co-distance of order 1, and so according to our definition, there's no topological order, and geometrically it means that only has a microscopic relative system. So the relative just means it's a cycle connecting different boundaries instead of being a loop. So this noble theorem is quite general that it also holds for so this. Well, I have E boundaries on these holes, which I call E holes, or arbitrary combination of M holes or E holes, or arbitrary combination of the boundaries. So whatever you do, there's no way to get topological order for a fractal event in a so the essence is that due to that, the system has a string-like logical order. So now, since there is no going 2D, so we start going into 3 dimension. Consider Z and topological order in 3D. And that's described by a topological quantum field theory, so-called BF theory or Z-gauge theory, that has a 2-form gauge field and a 1-form gauge field correspond to magnetic and the electric degree of freedom. So, and one can cook up a very concrete exact solvable model and error correcting code, which is the 3D toric code, and we consider the n equals 2 case, the D2 toric code, focus on this case. So this model is parent Hamiltonian has 2 types of stabilizer. There's X stabilizer defined on the vertex, and there is 6-body, and then on each plaquette, you have 4-body Z stabilizer. And then this model have a Z2 fusion rule that a pair of E particle can fuse into vacuum, and this E particle corresponds to a violation of the vertex stabilizer. And one can create a pair of E particles by applying E word line, Wilson line, corresponding to the E particle. And in the lattice model, it's a Z string. So this D tensor notation just means the tensor product of the configuration. And similarly, there's a Z2 fusion rule for the M strings. And this M string, they are violation of the plaquette stabilizers. So, and one can create a loop like excitation by applying X operator inside the loop. And so the worksheet of this M loop is an X membrane of X bridges for it should be concise. So then in this system, we just talk about the bulk property of the system. Now we want to talk about the boundaries of this system. So there are also 2 typical boundaries similar to the 2 dimension, but now there is some asymmetry. So you have E boundary, which could condense a E particle, which means the Z string can terminate on this boundary, and then you have the M boundary, which is the condensation of a string or loop excitation, which means an X membrane could terminate on this boundary. So then we can look at a logical operator of a 3D surface code, which is defined as you put the E boundary or the rough boundary on the top and bottom, and then you put the M boundary, or so-called smooth boundary, on the four sides. So this is like the TQFT picture of this lattice model. So the two logical operator is the logical Z string, and which intersect with the logical X membrane at the single point.
The videos on the slides are
in my convention, C always terminate at the E bound. The X always terminate on the M bound.
I was just remembering.
For this pose. So yeah, so the X terminate on the M bound. Z terminate. Yeah, that's it. Okay, so now we start to digging holes. We consider whether you can have a topological on fractals, but embedded in the 3 dimension. So we start with a very simple fractal geometry, which is called fractal cube geometry at C, which is kind of a generalization of the 2D surface topic. And similarly, we can define the fractal iteratively by defining the ratio between the system size and the hole, 3 versus 1, and then you have a level of iteration. And this kind of fractal we call it a simple m-dimensional fractal, just defined. So it is a fractal formed by just punching n-dimensional holes, which are homeomorphic to n-dimensional ball. So in this case, it's 3-dimensional ball. So yeah, so that embedded in an n-dimensional manifold. So however, in 3D, there an asymmetry. The two types of holes behave differently. So there are E hole with E boundary. So that could trap a logical Z string between a pair of E holes, and you can also trap a logical X membrane surrounding this E hole. So that actually could encode a logical qubit. So it might be useful for other purpose, but in the case of fractal, it will be a curse, as you will see. And in contrast, you can have a M hole, which holds with M boundaries. So then you want to mimic the behavior of this trap, like word line of opposite type, which is the kind of word line with E particle and the Z string. But you will fail because this loop is contractible, so you can continuously shrink it to nothing just by multiplying the Z stabilizers in the exact model. So that means the M hole does not encode any logical qubit, and that turns out to be a blessing for fractal. So first, we just discussed there's a noble theorem for any fractals with E hole. So it's similar to the 2D case that you can always find an order 1 size logical Z string that cross with the logical X membrane such that they anti-commute. So that means you have a microscopic Z distance, and the overall distance also microscopic, and geometrically you have a microscopic relative 1 system. So you don't have any topological order in this case.
I guess if you said you just had like real freedom, then let's say you only be like boundaries. Does that work, or are there still
yeah, we certainly thought about that. So Harry's proposal is that you can treat all this short string and some gauge qubits, and consider the whole thing as a subsystem code. But the problem is you need to measure this gauge operator, and then will somehow there this large hole, and in the end you will need to measure some gauge operator which is macroscopic of the size comparable to the system. So we could not measure that reliably. So yeah, that approach can still fail. And also when we define topological order, we will consider subsystem. Okay, so yeah, but in contrast, if you have this M holes on a single fractal, then you actually you can have a stable topological order. So our theory is that the topological order is on single fractal in 3D manifold with only M holes. So the reason is this. So here is the macroscopic logical operator, which already exists in the 3D surface code or 3D toric code. So we know that, but you ask whether there's any very short logical operator in this system, but the answer is actually no. So one can prove this. I'm sure the essence of proof here. We just consider the n equals k 2 case, the Z2 toric. So the reason is that there's no microscopic logical Z string because any Z loop can be continuously contracted. It's continuously contractible to identity. So the only class of a non-contractible Z string must be associated with this macroscopic logical Z operator. So, and this equivalent class of logical Z operator is described by the first relative Z2 homology. So this relative group just consider the boundary, E boundary where the logical operator can condense. Or you could think that you can reduce this to the usual homology group by identifying the whole E boundary into a single point and glue this edge into the single point and these two boundaries together. So that group is just a Z2. So they are single logical degree freedom. So similarly, the equivalent class of logical X operator is described by the second relative Z2 homology group of the dual lattice L star. So, and the corresponding boundary is the M boundary. And due to Poincare Lefschetz duality, sort of a generalization of Poincare duality in the present boundary, so this H2 is isomorphic to H1, which is also a Z2. So that just means the only class of non-contractible X springs must just be associated with the macroscopic logical X operator. Although this macroscopic logical operator could be has a far smaller than the usual 2D memory because it could be a fractal shape like this, but it's still macroscopic. So that just means there is no microscopic logical operator in the system at all, in contrast to the previous case. And we have a macroscopic distance and a macroscopic relative system. So that's the proof. Okay, so then we can look at the code properties of this code. So in this particular fractal, which has the size ratio, system size to whole size ratio 1/3 or 3/1. You have the Hausdorff dimension, which is 2.966, smaller than 3. So the total number of qubits you need also scale with this Hausdorff dimension, which is less than L cubed. And then the logical X operator has the shortest support, which is corresponding to a Hausdorff dimension 1.893. So the X distance is reduced. So instead of L squared, it's L to the 1.893. But the Z distance is invariant, still the system size L, because this Z string cannot terminate on this boundary. They are M bound of opposite time, so there's no shortcut. You have to go at least this distance. So the overall co-distance is the minimum of them, which is still L, so remain the same as the 3D particle, but if you reduce the number of qubits. And then you can construct a family of such fractal codes. So we consider more general fractal, for example, in 2D, you can define Stravinsky coupling with the ratio P over P and Q of the sequence and the host size. And then you can repeat this iteration, and then you can calculate the fractal dimension, and you can do the same thing for the 3D fractal cube. And for example, if we choose the ratio to be 6 and 4, then you further reduce the fractal dimension, smaller than previous case. And also you reduce the x distance, but the z distance and the overall co-distance remains the same. And finally, you could just tune this ratio such that, for example, you can choose a subclass to make the two ratio to be P and P minus 2. And while you increase P, you can continuously crack down the fractal dimension such that the it can asymptotically approach 2 plus each. So it almost has the same number of qubits as the 2D code, but it has some property of the 3D, some property of the 3D code, and you can keep the distance invariant. Okay, so we could also have a systematic understanding of topological order of fractals in arbitrary dimension. So actually, it's not too difficult to generalize. So we can do the simplest case of a Z and H theory that or the BF theory that you have in arbitrary dimension n, you have always a n minus I form gauge field and I form gauge field. So we call this kind of topological order a I n minus I in topological order. So then you can also construct exact sort of model of this I n minus I topological order, and we in particular we consider n equals 2 case. So you can define this family of codes with a Z2 chain complex. Here, this means I cell. This is I plus cell. I plus 1 cell. This I minus 1 cell. So in general, I can put qubits on the I cell and put the X stabilizer on the I minus 1 cell and on Z stabilizer on the I plus 1 cell. There, I can define some component which is generalization of the qubit 3D particle. So in this class of code, there's a logical Z I brain, the brain and the I dimensional that is described by the I's homology group, and the E excitation, the responding excitation, the E exciting was which is 1 dimension lower than the logical brain. Exciting minus 1 dimensional, and similarly the logical X brain is the n minus I dimensional, described by the n minus I homology group of the dual lattice, and the corresponding M excitation is also 1 dimension lower. So in the I equals 1 case, so it's a theory with the E excitation being positive, and then you'll have a string-like logical operator. So the corresponding chain complex is just the C2, C1 to C0. You put qubit on the edge. So this is very similar to the 3D Tori code we discussed. But if you put I larger than 1, you will have theory without the particle excitation and any string logical operator, which is a self-correcting quantum memory. It's stable even at finite temperature. So we consider then we can prove some theorem that that in the case that there is particle excitation and a string logical operator, this 1 n minus 1 topological order, you have a topological order that if all these holes are M holes. So the essence is similar to the 3D case, because this holes is an n-dimensional ball, and then it cannot trap any microscopic logical string, because this is able shrinkable. But the more interesting case is that in the model the self-correcting memory models that there's no string logical operator. In this case, you don't need to specify the type of boundaries. So either for E boundary or M boundary, you will still have a topological order if you at least we can prove in the case that it's a simple fractal that all the hosts at n-dimensional balls, topological equivalent to n-dimensional balls. So here is the essence. So the Z logical operator in this case is n-1 dimensional. So the Z logical operator is the I-dimensional sphere. But the whole is the n-dimensional ball, and its boundary is the n-1 dimensional sphere. So you cannot trap an I-dimensional sphere around an n-1 dimensional sphere. So you can always find some extra dimension that perpendicular to the sphere that somehow it can circumvent this code that can continuously shrink this to the sphere to the other side, which is of the whole, and then you can further shrink it to identity. And then similarly, for the logical X operator, which is the n-I dimensional, and it also cannot be trapped by an n-Y dimensional sphere, and always continue to shrink it. So you can never find any trapped microscopic logical memories. So that's why you have a macroscopic distance and stable topological order. Okay, so I already talked about the first part about the finding topological order and the quantum codes on fractals. So the second part, I will discuss how to perform fault-tolerant logical gates on these codes, and further their connection to emergent symmetry and topological defects, which are even more general. They can be existing much general codes other just than fractal codes, but they will be useful also in the context of fractal logical operations.
Previous one, I guess on their estimate of like actual resources. So I guess the most of the statements I think about but I guess in terms of like finite size logical performance, like actual, have there been any more helpful or at least even heuristic estimates?
So yeah, that's a good question. So I mean, in order to see the asymptotic behavior, so you need a few iterations, right? So if you cannot even perform the first iteration, dig the first holes, then you won't see that. But if you can dig first the largest hole and second largest hole, you start to see the function. So yeah, you can calculate the number of qubits, still use the fractal dimension to perform it's a very good approach.
So I guess let's say that we just take the first hole. So we have a pretty vertical take the first hole. Just in terms of like absolute multiple error rates, would you expect that the absolute multiple error rate would be like the same, or are there like entity factors that have finite size?
Yeah, we actually perform simulations. So actually, for one type of logical error, like the Z logical error, it's actually better than 3D fault. Just because it's closer to 2D. So this string cannot terminate on poles. It's like a maze. They have to kind of surround it and then actually improve the logical error. But for the other type, it will decrease.
I guess the other type anyway has a larger distance.
Yeah, a larger distance. So overall, there sometimes they just improve the inverse. Okay, so yeah, okay, let me continue about discussing logical gates. So since our fractal surface code is kind of based on the usual stringy surface code, but just digging holes. So the logical gates will be to some extent similar to the 3D surface code, and that has been studied in the literature. So the 3D surface code, if you take 3 copies of a 3D surface code, which I introduced before, but such that the Z string are aligning 3 different directions, Z direction, X direction, and Y direction. And in this case, you can perform a transversal logical CCZ gate. It is a transversal gate in the sense that you can write it as a tensor product of a CCZ gate between each qubit, each of the 3 qubits that align together in these 3 pockets. So you just can align these 3 codes together, and then there are 3 aligned qubits to just perform CCZ gates, and then it's a tensor product. And this works in the 3D surface code, but somehow it will be much more complicated in the case of fractal code. So in order to understand how to do logical gates, in the fractal code case, I need more kind of deeper understanding of the connection between these logical gates and the topological defects and symmetries. So here is so previously there has already been some understanding of this connection between transversal logical gates and the emergent symmetries in the topological orders. We consider a transversal gate, just discussed before, that in general it's a tensor product of unitary applied on individual sites between different code blocks. This transversal gate is more desirable because it usually doesn't propagate error across the system. So if error located inside J will still remain inside J. Or more generally, we consider some generalization of a transversal gate into some constant depth local circuit. In that case, the error propagation is also limited by light cone. So that's why these 2 types of gates are very desirable and they're fault-tolerant. And then we say it is a logical gate if and only if it's a preserved your code space. That's the definition of logical space, logical gate. HC is the code space. So now we want to connect it to symmetry. So we consider a generic topological order composed of multiple copies of a symmetric topological order or categories like this. So we also have a corresponding parent Hamiltonian, which can be split into a bulk and boundary part, which both sum of bulk and boundary stabilizers. And we say U is an emergent symmetry if I can preserve the bulk part of the Hamiltonian up to when you project it to the code space or ground subspace. So this emergent symmetry is has less requirement than microscopic symmetry, which you need to exactly preserve the Hamiltonian. But here I'm only preserving it up to projection to the ground subspace. So that also kind of preserves each term in the Hamiltonian up to the projection. So in the case without boundary, so this condition is equivalent to this condition stop. Basically, emergent symmetry is the sort of symmetry that doesn't necessarily preserve the Hamiltonian, but preserve your ground subspace. Here we consider sort of a more specific definition in the context error correcting code, but in general, I think people talk about emergent symmetry such that they are usually not the symmetry, microscopic symmetry in the high energy scale, but somehow they emerge the low energy and the non-wavelength scale. Furthermore, we say U is a global symmetry or zero form symmetry if it acts on the entire system. Or and more generally, there is some higher form or K form symmetry if it acts only on a co-dimensional K submanifold. So co-dimension K means the dimension is the total dimension n minus the co-dimension. The n minus k dimensional submanifold. And then the global symmetry is the case of k equals 0. So you apply it on the entire manifold. And in order for this emergent symmetry, which only preserve the bulk part to be logical gate, you also need to satisfy the condition that it also preserves boundary. So if you preserve both the bulk and boundary, then it will be a qualified logical gate. So yeah, so here is the notation that is preserve each boundary of the system. Then we talk about so there's further a connection between this emergent symmetry U and the sweeping of certain topological defects, and in this case some invertible defects, or sometimes called domain walls, by rho d. So the connection is this. So if I apply this emergent symmetry operator in certain region, but not the entire system, then the boundary of this region, there will be there will form some sort of domain wall or defect, which is denoted by rho d. And then if you sweep this domain wall across the whole system, that is actually equivalent to applying this emergent symmetry on the whole system. So applying emergent symmetry operator is equivalent to sweep defect. And in our context, it's important that this U, if you want it to be a logical gate, it should also preserve the boundary, which means that this invertible defect will condense on this boundary. So that's an important condition which we'll discuss a lot later. So this is sort of using the second code that information and physics. We can understand the logical information operation in terms of some physical objects, these defects. So you can further generalize this picture to a four-dimension K defect, which is responding to K minus 1 form symmetry. So it's acting on a four-dimension K minus 1 submanifold, and then while you apply only on a certain region, it's bounded with the four-dimension K defect. By this symmetry or this logical gate is equivalent to split this defect across the system. Now I'm talking about what's the definition of this invertible defects. It just means you can for any class of inverted defect, you can always find its inverse that two of them can fuse into the vacuum or into a logical identity. Nothing. So, and we can actually prove that sweeping of a general codimension K invertible defect can always be implemented as a constant depth local circuit, which we mentioned in the previous slides. So the proof is actually simple. So you can always just create a pair of a defect and its anti-defect parallel. And then you can annihilate the neighboring defect, which inverse of each other. So effectively, you can sweep the defect across the whole system in a single step. So that's a kind of a profound connection. So now, in our case of the 3D oracle, in particular, string copied 3D oracle, we also call it a stat code, which is equivalent to a Z2 cube topological order. There are two interesting types of emergent symmetries. One type is a one-form symmetry, which corresponds to sweep a four-dimension 2 defect, which is string-like. And this perform a logical CC gate, and we call the corresponding defect a CD defect. And in the later paper, we also call this type of defect a two-string because it's a string-like. And it has an interesting action on the excitation, such that if you have the M string or M loop excitation, when you goes across this tree string, we will attach some E particle on the other layer. So the M flux in the first layer will when across the string, there's some E particle in the other layer coming out at the intersection point. And this corresponds to by CZ gate on this 4-dimensional one submanifold or this 2-dimensional band, and that will map original logical X membrane to this logical X membrane comes logical Z string on the other lane. So this is sort of an interesting feature. And then there's another type of defect, CCC defect, which is a global symmetry, and there's a codimension 1 defect. So it's membrane-like. So when you sweep this membrane across the systems, you effectively apply the CCD gate. And it has the interesting feature that this defect, when there's M flux goes across this defect, it will become the M plus flux itself, but it also get attached with a CZ tree string. Or there's a hierarchy of a relation. So the CZ tree string appear in this relation, and that means the X membrane I mapped from an X membrane times a CZ map, which is the logical CZ gate in this case. A certain hierarchical relation. So now we will understand so this kind of thing has already been discovered in the Excel model, but we want to understand what's the essence from a deeper condensed matter or deeper FT point of view. Where does this effect come from?
So for the CZ, just to make sure I understand what exactly the action is, would apply transversal CZ in one horizontal layer.
Yeah, exactly. Yeah, and it's also important that you can apply it on this layer deformable. You can arbitrarily deform it instead of being just rigid in the XY plane. So that's the property of typical property of one form symmetry and a high form symmetry can arbitrarily deform subnet. As long as they belong to the same homology class, it's the same effect.
I guess this is quite different from like usually when I apply transversal, I would apply it on the entire.
Yeah, yeah.
Because this is the one point.
Yeah, yeah. So it's quite exotic, but yeah, it's also powerful. So in order to we first try to understand, what is defect tree string, which causes this one form symmetry, and the symmetry case we will first go down to 2 dimension, 2 plus 1, the 1 is the time direction, 2 plus 1 the G gauge theory. So a simplest example is we consider Z2 times Z2 picture. There are 2 copies of 2D toric codes, and we can make this type of a tree string by start from a trivial invertible phase, but decorate with a string-like symmetry protect topological state, or in the quantum information literature, it's called a cluster state, and it's Z2 times Z2 SPT. And then we can gauge the Z2 times Z2 global symmetry. So in this way, you can just cook up this CZ tree string. So here, by gauging means as we turn this global Z2 times Z2 symmetry into certain local gauge symmetry. An alternative view is that you can couple the system to some dynamical gauge view. So the equivalent. So just to illustrate with a concrete lattice model, we could start with a Ising model, which has these 2 types of terms. And you can see there is a global Z2 symmetry product of all the X, because they hit this D operator twice, so they commute. So the gauging can be just simply understood as some sort of operator maps
So I can map the original X operator on the vertex to a star-like operator on the edges. And then I apply a product of ZZ term, so that to a single Z terms on the edge. So that this is a gauging map. Besides, so this kind of so then the global symmetry equal to 1 is translated to the local Gauss's law that the product of this X equals to 1. That's like a stabilizer condition. But in order to make a finite dimensional Fourier space, you also need to put some additional gauge constraint. We also call zero flux constraint that the blockade Z term has to equal to 1. So when you do this map, we'll make the fixed point paramagnetic Hamiltonian into a torical, which everybody familiar with. But if you have an external ferromagnetic interaction, then it's mapped to a single magnetic field, Z magnetic field in the torical, such that you no longer have a zero correlation magnet. So then we just decorate this paramagnet with so it's 2 layers of paramagnet with a 1D Z2 times Z2 SPT, which also called cluster state with the 3-body stabilizer XDC. Then when you apply this map, we will find that this 3-body term becomes this 5-body term as a product of X and single Z on the other layer. So this red and blue just shows the lattice on the 2 layers, and I didn't draw the grid on the red layers. But these kind of terms now couple different layers, different torical layers, and it's exactly the CD string we're talking about. So and then you can see that if I pass an X string, in order to commute with all the terms in these models, it will enforce that a Z string coming out. So that gives the picture that the M2 times E1. So the M2 string, the word line of M2 now, there's the E1 word line coming out after passing the defect. And similarly for the other layer, M1 becomes M1 times E2. So that's the any automorphism induced by this defect. And then you can check that if you sweep this twist string, it's exactly equivalent to apply transversal logical CZ gate between each pair of the blue and the red dots. So and that CD string will map this X string into X times Z. So if you finish this sweeping. And then we can do exactly the same thing to 3D. So everything is the same. We start with invertible paramagnetic states in 3D, and we still decorate a string like SPT state, and we do the gauging, and then you will get the twist string in 3 dimension, and this works in arbitrary dimension. So in this case, you will see that if you have an X memory goes across the CD string, then a Z string had to come out. So just to remind you, so this gives you the automorphism I just talked before, that the M1 string gets attached with the E2 particle, and in the logical picture that the logical X memory is transformed to the product itself and a logical D string, which is satisfy the definition of a CZ gate. When you work with the example you gave, if you apply this, you would essentially be doing like transversal CZ. Yeah, and that would be like the normal transversal. Yeah, in 2D it's a global symmetry and a transversal CZ gate. In 3D, there is also a transversal CZ gate, but also they apply some. Okay, so then you can do the similar thing to produce the codimension 1 CCD defect. You just decorate with this trivial phase with 2 plus 1 Z2 times Z2 times Z2.
SPG. And you will construct a similar lattice model, and you see all this corresponding automorphism I just talked about, and then the logical gate. So just to highlight that for this CCD defect, this M loop one, it goes across it, it will produce the CZ string, CZ tree string, and that respond the word sheet of this CZ string is exactly a CZ membrane operator. So that completes the logical CZ defect.
Which SPG is it? Is it the type 3?
Yeah, the type 3 cosine. So sorry, I didn't show the actually. Yeah. So and now we also want to. It's important to understand also the condensation property of the defects on the external boundary. So because we want to preserve boundary to perform a logical gate. So yeah, so we want to check whether this defect would condense on this boundary, on the external boundaries in our code. So first, in case of 2 copies, the 3D toric code. So we can see that the CZ tree string can indeed condense on the boundary if the boundary is as a mixture of 2 types. So in one layer it's an E boundary, the other layer it's M boundary, or you just interchange it. So you can see this easily from the definition of the CZ tree string, because the CZ tree string does nothing to the E excitation. It will map the M excitation to the product of the M excitation times E excitation in the other layer. So it's sort of a permuted notation of this boundary, but it's essentially just a basis change. It's just choosing a different basis of the same boundary. Why? Because I can multiply these 2 things that, because 2E refers to identity. So I again rewrite it into E1 active. So it just did nothing to the boundary to preserve the. So this CZ string can actually condense on this kind of mixed boundary. So in our case, we finally need to do a logical CCD gate. So we have to consider 3 copies of oracles. Then we can see the CZ string between acting on any of the 2 layers. It will condense on the type of boundary that has 2 copies of M and 1 copy. So basically applying the same relation here, just S2AC only act on layer A and layer C. So the middle layer doesn't change. So just apply this relation, you will see that this CZ tree string coupling layer A and C will condense on this mixed boundary. And that's exactly the boundary in the case of the usual 3D toric. You'll have 2 M boundaries, 1 E boundary. And then we want to check whether the CCD defect could condense on this type of ME boundary. So the answer is also yes, because you can again apply the definition of the automorphism of the CCD defect. So what it does is so first I rewrite this boundary in a redundant way, because I know the CZ tree string S2 just condense on the boundary, so I can rewrite it to put this object into this location. Then I apply the automorphism, so I can map this M in layer A into the CZ tree string in layer B and C. And then I can again apply the fusion rule of the tree string, because it's invertible defect. 2 of them fuse into vacuum. It's inverted itself in this case. So then you can just combine these terms. You get what you start with, and you can also rewrite it into the minimal basis. So actually preserve the boundary. So that's the reason why in the 3D torical case, one chooses a boundary of this type. But in our fractal case, we have to choose all the whole boundary to be M type of boundary. So the whole boundary has to, and we consider 3 copies, so the whole boundary has to be an M boundary. So 3 copies are empty. So then you will see that when you apply the operator, the automorphism on the excitation, there is simply no way to rewrite this new notation back to the original. So in fact, you produce an exotic boundary. So which is denoted by m times s2. So we could now try to understanding the condensation property of this new exotic ms type of boundary. In terms of actually it can be considered as a composite boundary, which is you attach this CCG defect S3 on the usual MMM boundary. So you can consider it as a composite boundary. So then you could try to check what's how this excitation, whether they could usual excitation, whether they could condense on this composite boundary. So you first pass the usual E particle and the M string across the CTT defect, and the E is preserved, but it's again E, but the E particle cannot condense on the M bound, so it could not condense on the composite bound. And then this M is transformed into the product of M flux with the in addition also there is a CZ free stream. So it's a composite of the M flux and the CZ free stream, and that could also not condense on the M bound. So in sum, that the usual E particle and neither the E particle or the M flux would condense on the new exotic bound. But instead, a composite of the M flux and the CZ, they could pass through this CCZ defect, and they are transforming into the usual M flux, and they could condense on this one. So the condensation property is that only a composite of the usual M flux and the new CZ free stream, the composite of them can condense on this exotic one. And in terms of a logical gate, that logical operator means only a product of the logical X memory and the CZ memory could terminate on this exotic one. So it's sort of beyond some usual Lagrange subgroup picture, which is the condensation condensed excitation will only subgroup of the usual E and M excitation. But here it's not in that picture.
That's interesting. So, do you know how to translate in terms of maybe field theory way of thinking? Like, so let's say maybe M string will correspond to maybe 2-form B field, is it? 2-form B field.
2-form, yeah. Yeah, yes.
That's the surface operator.
Yeah, surface
operator.
Yeah.
And CZ string will be some other, maybe some other operators. You know how to write it.
How to write down?
Yeah.
Well, in this exact solver model, it's just a CZ operator.
Because earlier you were showing the BF theory.
Mm-hmm.
You know how all that corresponds.
Yeah. Yeah. I know that you could. I may discuss with you later. So it's more complicated. Yeah. But you could write.
I guess
into the Lagrange.
I think I have a comment to say that we also study similar exotic boundary, right? Like similar to this. It's neither condensing just electric particle, nor the magnetic strings, but some combination of the M string.
Yeah.
Some composite out there basically. I'm not sure what the UZ CZ string is some kind of composite particle bound. Yeah, maybe I can make it.
Oh, I see. Yeah, I mean, you could also think of CZ string as some sort of condensation of E excitation. Right? You can think of it as
more like a 2 times E or something like that. But neither condense just E1, E2, but only both E1 and E2, something like that.
Yeah, we should discuss. So yeah, now we have all the ingredients to discuss how to perform logical gate on this fractal code. So there are basically two steps. So the first step, you again apply a transversal CCZ gate, just like the Oracle case, but it's equivalent to sweep the codimension one defect across the system, the CCZ defect across the system. And the things that then okay, so the CCZ defect does condense on the external boundary, just like the 3D particle, because it's some sort of a EMM or boundary. We said it condense on that. So it doesn't change the external boundary. They still look exactly the same. But the internal hole boundary, was the MMM type. Now they are changed to this dot boundary, just discussed in the new slide, and they become this green-like brown boundary. And what they look like in the exact solvable model is that the original X stabilizer now becomes an X on the boundary, becomes a product of X stabilizer times the CZ operator corresponding to the other two copies. So this is copy A, but then there are CZ operator in copy B and C. So you get a model that is not the usual stabilizer. And here we implement we call it a transversal logical map, in the sense that it does some logical operation, but map your code space to a different code space. You create a new code. Okay, so the second step is exactly you have to map the new code back to the original code space. So there's an extra operation you need to do. Actually, there are many different ways. There are there are unique ways to do that. There are several different ways, and here I'm just talk about one way that we first came up with, which maybe not the best. So how do we do that? So we have this sort of new code, which is store our logical information side. But then we took some additional fractal, which is like an ancilla that they initialized in the 0 state, and then used for logical information. But we apply a so-called lattice surgery that we can apply neurons or measurements of this interface stabilizer and the correct error, such that you can glue these two codes together into a single code and while preserve the logical information. And then you can split this code again, and such that you can transfer the logical information to the ancilla copy, but with the usual boundary. And you do that by you measure out the first copy in the X spaces, in the Z basis. So it depends on your measurement result. Either whether it's 0 or 1, you will apply some correction to the ancilla copy. So condition on that, you can recover, you can transfer the logical information to the ancilla copy. While back to the original code space, such that you have the original normal MMM block. So just to, and you need to have 3 ancilla copies to transfer information of all the 3 copies in the original code. And that has the protocol has space overhead of order D to the 2 plus epsilon dimension. So instead of a D cube, the 3D protocol. And this protocol has time overhead order D, but we are also studying that more powerful protocol that can do this process with order 1 time. So the overall space-time overhead will just be this. And then also interestingly, you can also have apply the transversal CZ gate in a single shot in time overhead order 1, because you could choose a sub-manifold that you apply the CZ such that this sub-manifold doesn't have any intersection with this whole boundary. You won't change the whole boundary at all.
So that shows the flexibility of higher form symmetry as a logical case. So this is just one simple example, but in some other cases, especially content LDPC code, they will become more powerful. But I won't talk about that today. So how much time does
Take your time.
Take my time. Okay. So
Could you comment briefly on the one?
How to do that? Okay, so it's complicated, but essentially, we want to use the single shot error correction property of the 3D code, but somehow they also exist in the track. So in this sense that this 2 plus epsilon dimension is even more powerful than imagine you have a non-Abelian topological code in 2 dimensions. There you could also do universal gate set, but take order d type always because you need to grade this thing along. But this could be more powerful than non-Abelian. Whereas realization is much simpler than just stabilize. Yeah, so that's somehow there are lots of new stuff. Okay, so
maybe you can implement universal gate set.
Yeah, you are right. So there is no universal transversal gate set, but we can perform code switching between these 3D code. Yeah, I forgot to mention that I already show how to do non-Clifford gates, but you also need to do Clifford gates, right? So and that will be done with the usual 2D service code. You can do all the Clifford gates. Then you need to switch, do a code switching between them, but you already did the code switching between this new fractal code and the old fractal code, or they did something like that, code switching. And you can also do code switching between the 3D fractal code and service code with a dimensional jump through some measurements. And that's how people do universal quantum computation with 3D or code or color codes. It's similar.
Yeah, the dimensional jump is
All the one. That's really use the single shot error correction. Yeah, which is the
both ways.
Yeah, both ways. But we still we are still working on that. We think it works. So okay, I'm done with the fractal codes. Finally, we are already seeing how powerful this 3-string and this high form symmetry and this boundary in fault-tolerant quantum computing. And finally, I just want to briefly discuss just to better understand the nature of these 3 strings and the responding high form symmetry. So in a more general 3 plus 1D G gate theory, which this G doesn't have to be 3-2 theory. It can be a non-Abelian group. So the most general construction. So basically, there are 2 in the paper we actually have 3 constructions. Here I talk about 2 construction of general theory of this 3 string. So one is through layer construction. The other I already talked about in the simple case by this decorating 1 plus 1D SPT state and gauge. But it could be more general for non-Abelian gate. So the construction is like this. So we already see that this 3 string exists both in 2D and 3D, right? So then you ask why there exists in both cases. It turns out you could construct the 3 string in 3D just from the 3 string in 2D. So through some layer construct. And here is the essence of the layer construction. So here we consider an example of a 3 plus 1D Z2 gauge theory, the Topological, with bosonic charge. And then what we do is we condense the pair of E particles in neighboring layers. And in general, it's just the charge and its anti-charge in the neighboring layers. And in this way, the charge will be mobile and become deconfined excitation in 3D. So why? Because a charge would fuse with a pair of this condensed pair, and then another E charge will kind of spit out in the next nearest neighbor layer, and in this way you can make the E travel across different layers, and then they can also travel in the plane, so they become deconfined. So because you condense the pair of E particle, they're sort of in the vacuum, so you should not be able to detect them through remotely through some grading procedure. So if, for example, if you have the M particle that goes around it and then pick up some phase, then you can see this condensed pair. That's kind of in contradiction. So this condensation will force this M particle to be confined together and form a string-like excitation in the 3D case. Because now, if you braid this string with this particle, it will braid together with both the particle in both layers. So the phase get canceled, so you cannot see this condensed particle. So yeah, so this condensation process will force the flux to be confined into a string. And similarly, if you have, we can also consider 3+1D C2K theory with fermionic charge, and you condense fermions in neighboring layers, and you will also produce this 3D fermionic torque. So the procedure of constructing the tree string will be you figure out some 2D tree string, which is much well understood. There are some like basically defect that has alien permutations in 2 dimension. They are well understood in 2D. And then we put that into one of these layers. And then we do a layer construction to condense the neighboring particles. And you get both particle and flux, and you will automatically get a tree string in the 3D theory. But it's not always successful because these tree strings has to satisfy certain compatibility condition. So let's see what's the compatibility condition. So imagine that we want to embed the ENM twist, responding to the usual people call it twist defect or Marana wire. In 2+1D toric C2 gauge theory or torical, and we promote that into 3D. So the answer is that if the 3D theory has bosonic charge or the usual 3D torical, that's impossible because this M flux at cross this EM twist string. So in this layer where twist string exists, the M will become E. Then you kind of broke this flux. And that violated the flux conservation, and also violated the consistency of our layer construction. That you have to force all the M particle to confine into a string-like excitation. So this is not allowed. So then in conclusion, that the tree string in the 2+1D gauge theory should correspond to certain flux preserving automotive, so that it should not change the flux excitation. So we have some examples in abelian case. There, if we consider we're condensing fermions in the neighboring layers, we can look up 3+1D Z2 gauge theory with fermionic charge, or the 3D fermionic torical. Then you can actually embed the EM twist into one of the layer and create some tree string in 3D. So what this tree string does is it will map this M flux into itself plus some extra fermionic charge. But if you think that this in 2D, the automorphism is just M goes to E because M times side E. But the fact that you're condensing the fermions makes this possible in 3D. But as you see, this is a flux preserving automorphism, and the flux is kept the same. And then the other example is just CZ tree string we just talked about. It also preserves the flux M1 and M2. But we can generalize this to arbitrary gauge, discrete gauge G, and including the non-Abelian case. And in the most general case, the point charge in the G gauge theory is a representation of the pure charge, pure point charge is the representation of G, and the flux label is labeled by the conjugate class of this group element G. And if you compactify the 3D theory to 2D, and this flux loop just become a flux particle. So in 2D, flux is also a particle. And then in general, the flux loop could also carry charge. So you have a more general object that there's a flux loop labeled by G conjugate class. There is also a representation of the centralizer of G. So this pi G is a representation of the centralizer of G. And then if you compactify the 3D theory to 2D, you will see it becomes a diamond. So it's a composite of charge and fluxing. So now again, we take some tree string in 2D, which permute aliens, and then embed it in 3D. And then what we need to do is we condense the pure charge and its anti-charge for our neighboring nodes. And that will give us the tree string in 3 dimension or even higher dimension. So if it satisfies 2 conditions, the first is the flux preserving of automorphism we just said. So it doesn't change the conjugate class of the element G. So this will give you some tree string, but it may not guarantee the tree string to be topological, which I will explain what it means. But there are also the second condition, which is stronger. That so it says that independent of the charge in your original excitation, this tree string will always attach additional charge, Abelian charge, sigma G, which is the central representation of the centralizer of CG. So the second condition is stronger than the first, and that will make sure that the tree string is topological. So yeah, for the Abelian case, they also satisfy this condition. So in the paper we study examples like in both DN gauge theory and the A6 gauge. And there are some examples in A6 gauge theory that the tree string satisfies property 1 but not property 2. So we say they're geometric geometric tree string. So here is the example. So the A6 theory, we can find some automorphism in both 2D and 3D that max it will change your charge by an additional charge, but only one the flux is only one the charge is the original charge is I3. But if you have other type of charge, then you won't get attached by this additional charge. So this means so if I start with a certain composite object, a flux with some additional charge across the tree string. So only when this charge, the point charge exactly cross with the tree string, you get attached with another charge. It becomes a different charge. So, but somehow if you travel in a different geometric path, such that this point doesn't cross with it, then the charge doesn't change. So there's sort of the transformation actually depends on the detailed geometric path instead of being fully topological. So that's kind of a weird situation. So we call this geometric history. It's somewhat echo like fractals theory that although you are building the theory with like TQFT ingredients, it's layer construction, but it produces some sort of object which is not topological. Okay, so So there is a second construction, which we will just talk about, but in the more general setting. So we consider 3+1D trivial bordonic G symmetric phase and decorate with the 1+1D bordonic G SPT, characterized by the second cohomology. Then we gauge this G symmetry, so we will get some invertible 4-dimensional one defect, this P3. So there's a nice dimensional reduction, or we call it a wrapping picture for to understand this. So if you have a flux group labeled by the condense class of G, and then you have a 1D SPT characterized by a second group cohomology. Then when you pass through it, because this three string is some invertible defect, you can just split it off into a bubble. So basically, if you reverse this picture, it gets kind of combined with the string, but you get split off. You get a loop just surrounding the flux, and then you can use a dimensional reduction picture that this sigma G is just a set product acting on the second group cohomology to give you the first group cohomology. It's essentially dimensionally reduction of the 1D SPT to a 0-dimensional SPT threaded by a G flux. And that thing turns out to be equivalent to a 1D representation of the centralizer of G. And since it's 1D representation, it's always an abelian charge. So then if we start with a G flux G, and then you will get attached with this abelian charge. But even when you have some additional charge on that, you will just get attached with the additional charge. So this procedure will always give you a topological QC as independent of geometry path. And finally, I want to so my collaborator further generalized this wrapping picture to the codimension 1 defect in the 0 form signature. So it's the same wrapping picture. You have a G flux, but you can pass through some 2+1D GSP, some gauge version of that. And what comes out is exactly a dimensional reduction of this 2+1D GSP threaded by this G flux, threaded by this G flux, and that is exactly this P3. So there is a hierarchy picture which we see why the CZZ defect give you the CZ defect one and flux pass through that. So that's a general picture, and the example we consider was a special case of that. Okay, so here's the summary and the output. So we show the notable theorem for topological order of fractals embedded in 2D, and then we prove the existence of a topological order of fractals embedded in 3D and higher dimension. So the topological order exists if the whole boundary condense string of higher dimensional memory excitations. While it doesn't exist if the boundary only allows particle condensation. But for the self-correcting model, it exists independent of the boundary types. So then we show the existence of a non-Clifford logical CZZ gates 3D fractal surface codes, and with the space overhead order D to the 2+2, and the current time overhead is order D, but hopefully it will reduce it to order 1, 2. And this could circumvent the space overhead implied by gravity and holding form. And interestingly, there is a global emergent symmetry corresponding to this transversal logical mapping applied, and the new exotic gap boundary connecting both the combination of loop and the tree string is discovered. And then the general understanding of tree string is 3+1D gauge theory, including non-linear gauge theory. Mathematically discover this on macroscopic relative systole in fractals. Yeah, so that's basically the summary. Yeah, thank you for your attention.
Thank you very much. Thank you for your nice talk. Very interesting results. Any questions from the audience? I know. Zoom.
Considering we don't know how practical it is.
Yeah, I definitely thought about it. I haven't produced any thought about it. That
Because it's a 2+1 space time, it's like this, right?
yeah,
I need space to things that
yeah.
trivial.
I agree. To some extent, you can think of this fractal codes as some defect network, fractal defect network. So have a similar to those fractal construct network of defects.
The
Then you
model
can-
itself is not uniform, right?
Yeah, it's non-uniform. Yeah, that's different. But you can also think of a space-time version of that.
Yeah.
That's definitely. I think that it could be also powerful for quantum function.
Any question from the Zoom? Okay. So the defects so far mostly is considering invertible defects. So maybe non-invertible defects, you expect something interesting to think about.
Yeah, I guess so. So if you have a non-invertible defect, then this splitting is not a lot, right? But you will get some
Yes.
additional line
That's right.
between and
Yeah.
superposition of that. I think that's
Yeah.
very interesting. So yeah, in general, I haven't found the interesting case that you apply non-invertible defect as a logical gate to that law. So there should be some interesting result.
Yeah. We can talk about that. Any question from the audience? So if not, I think we should thank Guanyu again. Yeah, thank you.